the network staff, the SAN staff, the database staff, the application staff, the unit, and everybody always points to the database. It's always your fault as the DBA. Why? Well, maybe you just don't have as much political clout as the rest of them, because you tend to not be heard from unless there's a problem. And that doesn't happen very often. But regardless, you tend not to have a lot of visibility into the applications that you are running. And as a result, it's kind of tough to be responsible for the performance of queries that you don't see. One of the other interesting numbers that you get out of Gartner Group studies is that 70 to 80% of all application performance issues come not from the database, but from code. If you've got bad code, guess what? You are out of luck. Identifying the bad code, that can be a bit of an adventure. That's one of the things we'll do with our performance intelligence tool. Application code change, generally you need to bring the evidence back to the developers, and guess what? A picture speaks 1,000 words, sometimes 100,000 words, depending on how the colors are. So, that said, frequently when people say it's slowing down, what is the knee-jerk reaction? Well, upper management frequently likes to throw hardware at a problem. Why? Because hardware will mask the problem, make things look faster until, oh, another week or 3 have passed, and the snowball has gotten bigger, and the performance problem has gotten worse, and hardware doesn't mask it anymore. What we need to be able to do is identify what the specific problem is and solve the problem rather than hide the problem. Here's what performance intelligence does. First, it measures time as opposed to a number of operations. Now, we will actually see in some technologies a number of I/O requests. Well, do we really care about the number of I/O requests? Well, from some perspectives, we do. I was to an application a few weeks ago where there were multiple queries that were making multiple hundreds of millions of page requests per hour. Well, guess what? Multiple queries making multiple hundreds of millions of page requests per hour. At that point, you can guess that reducing the number of I/O requests is going to have a favorable, positive impact. And in that case, we were able to bring the 100 million or page requests per second down to a couple thousand per query, which was made a lot of friends fast, as you can get. What we're do here is not only count the operations, but measure the elapsed time. It doesn't care if it takes a million IOs if it's coming back sub-second. You and I both know that it's not often going to be a sub-second operation, and when lots of people are starting to do it, then it starts to build up. Next, we're going to focus on the queries. Why? Because we want to know which queries are doing what. We take this little granularity and say, okay, this query is the one that's performing the 100 million IOs. We perform a continuous capture. What that means is that we are collecting this data all the time. We're collecting it on Saturday afternoons when the batch jobs are running, late nights. It's running at peak times, 9 o'clock in the morning when people are logging in. And we have the ability via an historical view to go back and look at it. We can look at trends. We can look at what the IO was at that point. We can look at what's happened to be. We can look at who was running what and when. And when John Smith calls and says, hey, we had a problem afternoon and everything was slow for me, you can go find out what John Smith was doing at 3 or 4 o'clock this afternoon. So what are we looking for? Within the scope of the warehouse, we're looking for trends, which is to say, are we starting to use more and more resources? We're looking for anomalies. Did we have weird things going on yesterday? We're looking for relationships. If I'm running this query a lot, I'm hitting a lot of CPU. As a result, what we need to be able to do is to slice and dice and pick this information up and do the deep drill down into what's going on. So performance intelligence analyzes all these data points across multiple dimensions and allows you to go in there and analyze the cube as appropriate. We have the performance intelligence to tie it together, this trend analysis, data correlation, expert advice, and that is you. You are the expert advice. The tool itself just points to the problem. You have to solve the problem. There's an alarm trail if, in fact, you want to set that up. A lot of reporting that is available and can go on an automated basis. The ability to set alerts and say, okay, if the average response time exceeds this, email or an alert. If too many users are log on, send an alert. You can also set up custom alerts. I had a customer in Boston who set a custom alert because they had an application that would log on, get stuck, and it would retry. And after a while, they'd have 800 or 1,000 logons. That one application, the automated application, that kept retrying, and guess what? They only had about 800 user licenses for that particular server, and as you can guess, that created a problem. So they built an alert in that every minute or so would go and ask, how many times has this user logged in? And if it was more than once, it would send an alert. Well, this, interestingly, the situation out almost as soon as the alert got put in. 15 minutes later, an alarm got kicked off, sent an email off to the DBA who said, guess what? This is already paid off. So awareness of the Sybase weight types becomes interesting. Weight type analysis is relatively new. The idea here is that when a statement runs, the user is experiencing some sort of weight. There are some resources that are using it. The types might be I'm waiting for the CPU to finish. It might be I'm waiting for a page to come off the disk. I might be waiting for a latch to be released. Looking at this, you'll see that an individual query may have multiple different wait types over the course of time and change it. 2 in the afternoon, we might be waiting for CPU. At 3 in the afternoon, it might be that the I/O subsystem is getting crushed and we're waiting for I/O. When the waits become chronic or excessive, you may see a performance problem or a pattern that you can go in and identify and resolve. This has a few dozen different types of wait types. In general, you tend to run into the basic ones. Note that if you are looking at the tool that we have and you are looking at specific wait types and you're wondering, what is a latch wait? You can simply click on it and it'll give you information on the latch wait. So, latch frequently unidentified issue represents a significant elapsed time bar in your wait time graph. Do I have a picture? I don't remember it now. So what is a latch? A latch is a non-transactional lock. What is it used for? Well, let's say you've got 16 processors and they all want to get into cache. Well, you can't have all 16 processors access to cache at the same time because what's going to happen is 3 of them get the same page. That's a bad thing. So the server use a thing called the latch, which is also called a spin lock. And it says, okay, whoever gets that spin lock first gets in first. And the other things sit there waiting for the latch to be released. Those of you who are technical geeks like me, note that that spin lock is exactly what it sounds, because rather than going into a wait queue, it does what your kids do in the back seat of the car on any trip over 4 minutes. Are we there yet? Are we there yet? Are we there yet? The spin lock says, can I now? Can I have it now? Can I have it now? Can I have it now? Until it actually gets it. But what you find is that when you buy spin locks, you frequently end up with high CPU as well, and there's a direct correlation there. And what these are there for is simply to keep processes from hitting each other. Note that if you're getting a lot of latch waits and you're getting a corresponding lot of CPU or something else, that's probably where the latch is pointed. You typically see latch waits under some specific circumstances. You have lots of DBCCs going on, cache is getting creamed and usually in parallel. Same thing with update stats. You missing an index causing scans of large table, at which point cache is being creamed. But, lots of other things can cause latches as well. Latches will control I/O buses. Latches will control cache. Latches will control access to network paths. Lots of other wait states are available, including network waits, lock waits, you name it. Spend figuring out what these are can be time-consuming and is usually not that useful. In general, what you find is that if you look at a query and at the wait states, it's generally pretty obvious what the problem is that you're trying to resolve. It says here 3 to 4 of the potential wait states show up in 80 of the problems. That should be 80% of the problems. Methods of wait type data capture. C has offered views into the wait type since about 12.502 when the MDA tables became available. Folks never became aware of the MDA tables. Gee, I've got the sysmon output. I don't really care about the rest of it. The nice thing about the MDA tables, though, is that you can suck a lot more information out of the MDA tables than was ever available for sysmon. For example, what was running, what it was hitting, what effects are of that running. And what this will do is bring the right stuff in and create the appropriate correlation. Note that running the MDA tables originally had bad rap in terms of causing a 5 to 10% CPU hit. I experienced that heavy a hit, although I've talked to a couple people who've claimed to measure it. I mean, it's a very difficult thing to measure because you have to associate it to the correct tasks and wonder, gee, did everybody start hitting the server a little bit harder? But with this tool, we don't turn on all of the MDA tables. We just turn a few of them on, and as a result, we find that it tends not to be an issue. Other problems with MDA tables, they tend to be a finite size. So for the first out stack. So if you're trying to pick up lots of information, by the time you get there, the information may no longer be in the MDA tables. There aren't any built-in tools for analyzing the MDA tables. At some point, somebody will publish a bunch of stored procedures for this, but there's an easier way of going about it, and honestly, I've recently become a fan of looking at these things graphically. Raw weight statistics, what goes into what tables, what the raw weight states are, no direct reference from within the tables, direct correlation out to the stored procs, what lines in the stored procs, getting the information out once it's gone in. The fact that selecting from the table means that you can't select the same information from the table again, it's gone. Lots of issues with those. So get out there, identify what the weight states are, what exists. You can identify some trends, but you really want to build this warehouse for yourself where you've got a packaged solution to look at things. Here's a particular problem that we resolved using this tool. Query. Note that you don't always know which is your problem query. Sometimes you identify a problem query and somebody says, Jeff, this is running slow. Other times they say the system is slow, go figure it out. Sometimes you end up with, hey, it ran fine in development, or ran fine in test, or it ran fine for weeks, and afterwards it's not. So if you're starting to look at this, well, gee, what's the first thing you do? Well, the query is running erratically. The first thing I